So now I want to prove the master theorem. Now I'm not going to prove the complete master theorem. I'm going to prove it for a special case, but it's an important special case that'll come up frequently. So I want to prove master theorem for the special case that f of n is literally a polynomial, right? And in fact is literally the polynomial n to the d. Right, so notice this is just f of n equals n to the d. There's no asymptotic condition here. It's always exactly equal to this. So let's begin with the recurrence relation that looks like this. So t of n equals a t of n over b plus n to the d. And we'll establish a base case, a really simple base case, where we'll just say t of 1 equals 1. Okay. So there's our recurrence. T of 1 could equal any constant we want. That's not relevant to what we're doing right here, though. All right, so it's not difficult, and I'm going to skip a lot of the gory details. It's not difficult to show the following, that this can be written after k recursions as a to the k times t of n over b to the k plus the following summation. So the summation goes like this. It goes n to the d times the sum from I equals 0 to k minus 1 of this ratio, a divided by b to the d, all to the power of I. Okay, so we have this as our kind of generic pattern that this will follow as we recurse again and again and again. So first what I want to do is I want to investigate the balanced case. So once we have it in this form, then we have to say, all right, what's the relationship between A, B, and D that give us the various cases? And first let's begin with the balanced case. So I'm going to call this case 2, the balanced case. And what determines balanced? Well, there's a couple ways of writing it, but in this context, the easy way to write that is that A equals B to the D. Okay, and if I go rewrite my critical exponent expression, that's what I'll get. So A equals B to the D. So I can rewrite a few things here and get something put together well. But essentially, what we end up with is this a to the k times t of n over b to the k plus n to the d times the following sum. The sum from I equals 0 to k minus 1 of 1 to the power of I. Right? Why 1? Well, because a equals b to the d. Right? So we get this, every term of the sum, the a and the b to the d just cancel out. Okay. So what is 1 to the I? It's just 1. It doesn't matter what I is. And, 1 raised to any power is just 1. And so this can simplify quite conveniently to the following. A to the k, t of n over b to the k, plus n to the d. Now times just 1 added to itself how many times? Well, exactly k times. So this is n to the k times k. Okay, so from here we can do our anchoring step. So for the anchoring step, what do we come up with? Well, we solve the equation n over b to the k equals 1, right? Which gives us n equals b to the k. Or k equals log base b of n, right? So these two are our anchored steps. And so now, we can continue down and we can say, all right, we've got now a to the log base b, this is equal of n, times 1, right? Times the amount of time it takes to execute a base case, plus now n to the log base b n to the log base b Oh, sorry, I messed something up earlier. I wrote n to the k when I meant to write n to the d, right? So this is n to the d. We'll put something else in there in a second. N to the d times log base b of n. All right, and so how do we interpret the left piece of this? Well, we swap the a and the n, right? That's a fundamental fact of logarithms. So we have this polynomial thing on the left that says n to the log base b of a, right? So that's the total effort that's consumed by recursion base cases. That's the recursion part, if you will, plus n to some power, right? So let's interpret d. So what do we know about d? Well, we know that a equals b to the d, and so if we want to solve this for d, we have to take some logs and things like that. And what do we end up with? Well, we end up with the fact that d equals log base b of a, right? And so you can tie this back to our original master theorem statement where we had the critical exponent kind of written out explicitly, and you'll see that these two conclusions are the same. But what this means is that this term here we can rewrite that in terms of a and b as n to the log base b of a now times the log base b of n. Okay, and so just for ease of reading, I can move this a little bit out of the way, and we have the following. We have an n to the exponent, to the critical exponent, plus n to the critical exponent times log base b of n, right? And so this dominates, and so the overall recurrence is big theta of n to the log base b of a times log base b of n. And notice, just for completeness, I've left that log base b of n in here, but that log base b of n, we could ignore the base if we like. And so because log base b of a equals d, we're done, right? This is it's the overhead complexity with a logarithmic slowdown. Okay, so there's our balanced case. We've now completed the balanced case. So now let's look at case 1. So we'll look at the overhead dominant case. Overhead dominates. Okay, and one way to rewrite the overhead being dominant is we can say d is greater than log base b of a, or this inequality, b to the power of d, is greater than a. Okay, so now let's go back to when we derived the pattern, copy it down, and then proceed. Right, so the pattern we derived was this. So I'm going to copy this down here. It did not copy well. All right, so here's our pattern expression copied down. And so now notice that this pattern on the right is a geometric series, right? So this formula here represents a geometric series. So let's just solve that. We'll write it out. We'll adopt the same anchoring step that we did before, so we can just use exactly what we had. And so this equals n to the log base b of a, right? Which you can pull directly from the balanced case analysis that we did. And so then this is plus n to the d times whatever the geometric series evaluates to, which in this case happens to be the following: a over b to the d to the power of k minus 1 over a over b to the d minus 1, right? And so this is just the geometric series. Now, what do we know? In the overhead dominant case, we know that b to the d is greater than a. Okay, so what does that tell us about a over b to the d? It tells us that that is less than 1, right? So that's here. And so in this case, we can inherit the fact from the geometric series that says no matter what, this converges to a constant. Okay, so no matter what, this expression, and I'll circle it here in blue, this expression is always upper bounded by something that's constant in k. Okay, and you can convince yourself of this if you like by actually sitting down and evaluating the limit of this expression as k goes to infinity. Right? So no matter how big k is, this is always upper bounded by some constant. And so what that means is that we can upper bound this entire expression by the following: n to the log base b of a plus n to the d times some constant. And I'll just call that constant m. Okay? So I know that this whole thing, the thing circled in blue, is less than or equal to m. So therefore, this overall expression must be upper bounded by m. So we already worked out this expression that says d, in this case, d is greater than log base b of a. And so that means this whole thing, I've got n to the log base b of a plus n to the d times a constant. So this whole thing has to be dominated by the n to the d part, and so it's big theta of n to the d, as desired. Okay, so now we've proved the second, or in this, I guess we call this for, case 1, the overhead dominant case. We've proved this case for the master theorem. So all that's left to prove now is case 3. The recursion dominates. So for the recursion dominant case, let's go back to our geometric series expression. Let's take a look at what we've got here. So we have, I'm just gonna copy this down here. So we've got t of n equals n to the log base b of a plus n to the d times a bunch of stuff, and I'm just gonna capture the piece that depends on k, and then I'll encode all the rest of it as a constant. So I'm going to encode all of this as a constant that's kind of irrelevant to our purposes, and then I'll just show this this a over b to the d to the k as the function that we care about. Okay, so this is equal to a over b to the d to the power of k times some constant, right? Times something that isn't going to be relevant to our analysis. Okay, so what does it mean for the recursion to dominate? Well, in the recursion dominant case, we have the following condition. We have b to the d now is actually less than a. Okay, and so we can use the same anchoring equations that we have before, where we can say, well, look, k equals in this recursion, k equals log base b of n. So there's our relationship there. And then let's investigate this piece. So I've got a over b to the d to the power of k. Well, this I can rewrite quite simply. Give myself more space. Can rewrite quite simply as just plugging in my expression for k. So b to the d to the power of log base b of n. Well, then this, I can swap the n and the exponential base here, and I can get n to the log base b of a over b to the d. Well, that equals n to the log, and you have to be careful with your exponents here, but log base b of a minus log base b of b to the d. Well, now here I've got a log base b of b to the d, which just equals d, right? I can take the d and put it out in front, and then I just have log of its base, which is 1. So this equals n to the log base b of a minus d. All right. So now let me plug this expression back in here and see what I get. So now I've got t of n equals n to the log base b of a plus n to the d times n to the log base b of a minus d, right? All that is up in the exponent, then times some constant, times something that just depends on a and b. Doesn't depend on k or n. So what happens when I evaluate this? Well, I get n to the log base b of a plus, then if I combine those two exponents, I have n to the d times n to the other powers. To combine the exponents, I just add the exponents together, and the d's cancel, right? One d subtracts off the other d, and I just have n to the log base b of a times some constant. And so then clearly the only term left that depends on n is that n to the log base b of a. So this is big theta of n to the log base b of a. And again, we're done.